All right, let's continue and finish up the little bit that we have left in this chapter. If you recall, last time we were talking about ways to disinfect, and we were talking about iodine and all those sorts of things. And now, what we want to learn about is identify advantages and disadvantages of temperature. And we'll talk about radiation, and we've kind of gone over a little bit of radiation, some of the things to look for your own safety. And then filtration is a really good viable option too. So heat, elevated temperatures are microbial. Low temperatures are static. If you go in refrigerators and things, you think everything is kind of just sitting there. It's actually growing. A lot of it is, and it's probably waving to you as you open the door. But the idea is you slow the growth down. That's the key. Moist heat is hot water, boiling water, and steam. Steam is just essentially boiling water under pressure. Dry heat is hot air, open flame, and that sort of thing. Pretty straightforward. Operates at lower temperatures and shorter exposure times with moist heat. Moist heat transfers that heat pretty effectively, and that's the deal. The sidal effect is the coagulation and denaturation of proteins. Dry heat dehydrates the cell, removing water. It does denature proteins. It can tighten up some of the conformations of proteins, so actually not doing yourself any favors unless you go up higher temperatures. But the problem is you end up burning or damaging things that might be going with it, like uniforms and things like that. So if we take a protein, we could change the conformation or the shape, and once you change the shape, it may block the active site, so it doesn't work or greatly reduces its effectiveness, or denatures it totally, so the shape can't be obtained, and that's pretty permanent. Moist heat, the magic number is 121 degrees centigrade for 15 minutes. You can go to a higher temperature, 125 for 10. But the industry kind of standardizes on the 15 minutes at 121. It's kind of strange that that's the bare minimum to get rid of spores, and so that's what we're doing there. And as I say, we usually put a fudge factor in there, like 125 degrees for 15 minutes, and it's just guaranteeing. Or you can go for 20 minutes at 121, something like that. It's whatever the place that you work at with their SOPs have determined that they want to use. Bacteria endospores are the ones that show the greatest resistance as far as bacteria is concerned, and the destruction of the spores are important. Clostridium species are the problematic ones. They're tough to get rid of. You know, the folks go in the Egyptian mummies and things like that. It's the curse. No, it's spores. And they germinate when they have nice warm bodies to grow in, and they return back to vegetative cells, and they'll grow and start producing toxins or whatever nastiness that they're used to doing. And it's no revenge, it's just dirty linen essentially. And it's been sitting there all those years, but that's what spores do. It's set up to kind of protect the genetic material, and it builds around it this peptidoglycan, which, you know, it's going to desiccate to some degree, but as soon as you add water, I mean, boom, there it is. It's ready to go and germinate. Just add water, you know, that sort of thing. So physical agents, a high temperature moist heat is more effective than dry heat. Boiling water, 100 degrees C, kills most cells. Killing spores and thermophiles usually requires a combination of higher pressure and temperature, and that's 121 degrees C at 15 psi for 20 minutes, and that will do the job. Vegetative cells of spore formers have the same susceptibility to heat as vegetative cells of non-spore formers. That makes sense. Pathogens have the same susceptibility to heat as non-pathogens. Fungi, protozoa, worms are similar in their sensitivity to heat. The viruses are resistant to heat. Tolerance extends from 55 for 2 to 5 minutes to 60 degrees C for 600 minutes. And because of the simple nature, it's sort of like a spore, but worse. The thermal death time is the shortest length of time required to kill all test microbes at a specific temperature. And again, that would require a grow out to prove that you killed all if you couldn't recover anything. Thermal death point is the lowest temperature required to kill all microbes in a sample in 10 minutes. And it's just, those are just standard definitions. Heat treatment of perishable substances must render the product free of agents of spoilage or disease without affecting the speed and cost of processing. And that's a pretty tall order. So we do have, of course, Louis Pasteur pasteurization and disinfection of beverages. Pasteurization is a technique in which heat is applied to liquids to kill the potential agents of infection and spoilage while at the same time retaining the flavor. You know, it's commercially viable. And so the special heat exchangers that expose liquid, it's a flash heat, 71 degrees C for 15 seconds. And the batch method, which they use for milk and that sort of thing, is 66 degrees for 30 minutes. And it depends on how large. Now, autoclave is quite an interesting. They have room-size autoclaves to very small desktop. We have both of those types at Wake Tech. And essentially what it is you're filling, we have a jacket, I have a steam generator that's off-site. It's not shown here in this diagram, but it provides a really nice and ample source of steam. It fills the jacket around it, so it's always somewhat warm once you turn it on, and then it'll flood the chamber where you store your whatever it is you want to autoclave inside the chamber, and floods it with steam and builds it up to 121 degrees C, 15 psi for 20 minutes, and you'll have nice and sterile. Now, what you put in there are materials, if it's dry type of materials like scalpels and things like that, and you put them in a wrap, or you can leave them out in a plastic container and that sort of thing. But you can vent the steam very quickly. But if you have a liquid and you don't want it to boil out and end up with an empty flask, you vent it very slowly. And so some of the gives and takes about working with steam under pressure. But all those things have been worked out, and they're quite manageable. So there's the autoclave, pretty much straightforward. It has all the characteristics. It's usually controlled by a microcontroller, so the ramping up and all that stuff is handled programmatically, so you don't have to do anything. And then all the equipment inside handles the shunting of the steam and all that. So it's just a matter of programming and making sure that when you take your samples out that they don't solidify on you. Put them in water baths and things to keep them until you actually work with them. But you can see in the diagram it's the steam, and then we vent it through an ejection area. And it's pretty straightforward, and it's all controlled, as they say, by a microprocessor. So from the user perspective, it's pretty easy. Some maintenance and having a steam generator are some of the requirements. I have used pressure cookers out in parking lots at some of the smaller schools that I've taught at that don't have autoclaves in order to make some plates. Today, I would guess I'd be considered a terrorist and be taken out and shot, I guess, out behind school if I were to take one of those. It's just amazing how the change of times, that was totally acceptable at one time for me to use the autoclave out in the parking lot with a long extension cord, and that way I could run it and put it on things to autoclave plates, but not anymore. So we're all familiar with the methods of incineration, Bunsen burners and things like that, and hot air ovens. We don't have one of those. Well, maybe we do. I haven't used it, but it's programmatically controlled, and sterilization requires exposure to 150 to 180 degrees C for 2 to 4 hours, and the temperature is maintained. And the same sort of thing is you can just put things like that. Principal benefit of cold treatment is to slow the growth. It just retards the growth. I mean, everyone kind of knows that. I have put microbes at -70, and there is a way to freeze your samples, or you can lyophilize. Lyophilizing is taking a sample from a solid that's frozen liquid and sublimes, so the moisture leaves and goes into this dry material, and that's lyophilization. And bacteria cultures retain the viability for a long, long time once you lyophilize the strains. I have many strains done that way. So the lyophilization, that's how you spell it. Combination of freezing and drying. Pure cultures are frozen into these little teeny vials, and they work, and they're able to all you have to do is re-wet them with a usually growth material and let them sit, and then you can put them on plates and they'll grow out pretty nice. Radiation, we've already talked about this. Gamma, X-rays, UV radiation, all of which the gamma doesn't leave a residue. X-ray doesn't either, unless there's materials in there that retain that sort of energy forms, and it can be residual. And UV is causes thymine dimers and that sort of thing. It's a direct effect. So what we're doing when we use the gamma rays or UV or X-rays, it's increasing the amount of frequency, energy, and the energy is so high it just pokes holes through everything, like the gamma radiation. It doesn't even stop to see the damage. I mean, it just blasts, boom, and it's usually kills everything it comes into contact. UV, of course, is the thymine dimers, where the two thymines now bind to each other from side to side. You can see where the red marks are, and the editing system will, the DNA editing system will edit that out. Unfortunately, our DNA is read in groups of 3, and that causes a frame shift, and that really puts a monkey wrench in the system, as we've talked about before. Another way to effectively remove microbes is to filter. Now we can use ultrafiltration. It all comes down to pore sizes and being able to filter things. The only kind of drawback to using filters, of course, the filters get clogged, and once they get clogged, then they're of no use. So there are devices in the laminar flow that constantly washes the surface, but it's still doing ultrafiltration. You can have hollow fibers. This is an ultrafiltration system with hollow fibers, the systems of those, and it goes from one end to the other, and that's the process of filtering. So it filters through a hollow fiber, so you're going from one flow area to the outer part of the flow area that has to go through the pores, and then that, of course, is now sterile, and you have an RO system that takes it out and that sort of thing. But it's all about how small the pore size is in terms when you say something's sterile. Well, is it viruses passing through it, or it really depends on that. The smaller the hole, faster clogs, and very, very expensive as you get down in there. We have things that we can use for air. We have HEPA filters, and we filter air handlers and aircraft and various hospital rooms and surgical rooms for laminar flow hoods and things like that. We do use ultrafiltration for water purification, and I have sterilized. There's certain chemicals that are really sensitive to heat. I couldn't autoclave it. It would destroy the nature of it. So I'll filter it, and then I'll add it to media after it's gone through the heating cycle to add it in. So there's all sorts of ways you can do these. The common one is you got a filter. It's a fritted disc. You put a filter paper on there, and you filter whatever it is. It holds the bacteria, and the elutant that comes out through will be sterile, and you can have that for whatever the purpose. But there are even simpler ones that can fit at the end of a syringe, and you just push the liquid through, and what comes out is sterile. So osmotic pressure is done by salts or sugar, and it causes plasmolysis. In other words, bacteria pretty much don't like that, and they'll either shrivel up. It depends on procedures, but pickling, smoking, and drying have been used for years to preserve foods. Osmotic pressure is never a sterilizing technique. It's a way of I don't know, adding a certain population of bacteria that maybe are less harmful, reducing the numbers, and it tastes good, I guess. I don't know. I don't ever use that. So we also now want to look at chemical control agents, chlorine, and some of the other types of compounds. Hydrogen peroxide agents, they work quite well. Heavy metal type of agents, we used to use mercury, which we don't do that anymore. We found out it was toxic. The aldehydes, we use for embalming and that sort of thing. Ethylene oxide is probably a really high-end one. It's quite dangerous. It leaves residue for a period of time. So chemical agents occur in liquid, gaseous, and solid states. They range from disinfectants and antiseptics to sterilants and preservatives. Aqueous solution, the chemicals dissolved in pure water as the solvent, and sometimes they're not very soluble, and that's a problem. Tinctures are chemicals dissolved in a pure alcohol and or water alcohol mixes, and just trying to get to work out the solubility of those things. They usually leave a residue in those types. So one of the first chemicals to be used for disinfection was phenol, first used by Joseph Lister in the 1860s. Standard for most antiseptics. Phenol derivatives called phenolics contain altered molecules of phenol. And antiseptics, you can look at the chemical structures. I just wanted you to kind of see what sorts of, that's a phenolic ring there with a hydroxyl group, so it's a cyclic structure. And then we have aldehydes like glutaraldehyde, formaldehyde types, and ethylene oxide. This is really very reactive, and you put a double bonded oxygen, it makes it even more reactive. And so those are common things that we use. Selecting microbial chemical is rapid action even at low concentrations. Solubility in water, broad spectrum action, penetrating of inanimate object surfaces, and resistant to becoming activated by organic. Those are the idea. It's a give and take. Those would be ideal, but it's a give and take, so it may not always work out that. Shouldn't be corrosive or non-staining. That wouldn't be good if you put something that turns a bright yellow or something. Sanitizing and deodorizing properties would be nice. Affordable and readily available. And of course, no chemical fits all of these or just some of these. Germicides are evaluated in terms of their effectiveness in destroying microbes in medical and dental settings. High-level germicides kill endospores and can be used as sterilants. Those are very expensive and have to use exactly a certain standard operating procedure. Intermediate level germicides kill fungal but not bacteria spores, and low level germicides only vegetative types of cells. It only cuts down a percentage. Factors affecting germicidal activity is the nature of the organism. Of course, it's its composition, nature of the material being treated. In other words, if there's bioactivity and it takes up its active site, so it would decrease its functionality. The degree of contamination it's able to do, time of exposure, and the strength and chemical action of the germicide itself. The chemical strength, dilutions, a small volume of liquid is diluted in a larger volume, and like chlorine, I use Clorox and I dilute it parts per million, and it's a very effective spray. I use that. That's usually what I use if I travel anywhere right now. It's guaranteed, absolutely, when you're 100% guaranteed you want to kill whatever it touches, a Clorox solution will do it. It's pretty strong. Length of exposure, require adequate contact time, composition of material being treated, smooth objects are more reliably disinfected with pores or pockets. In other words, it just has bioavailability and access. Large amounts of organic material can hinder penetration. Again, as we already talked about that, it gives it active sites or things to interact with, such basically diluting the germicide that you're using. Large amounts of organic material hinder the penetration blocking it, and adequate cleaning of instruments and other reusable materials must proceed. We always use clean instruments. It kind of goes without saying. So required concentrations, again, these are just sort of industry standards, but would be subject to whatever SOP where you work. Do not commit this to memory or anything. It's just a way to kind of look at things. If you're comparing tuberculosis and you're using chlorine, it's 50 parts per million. Amoeba histolytica, protozoa, it's 0.1 parts per million, and hepatitis is 3 parts per million. So bacteria, you're going to have to dose it pretty good, but look at the time frames, 150 minutes, but pretty low concentration. Ethyl alcohol, staph, 70% for 10 minutes. That's what I was talking about when you get a shot. You soak the area down, 70% concentration, and they wait 10 minutes. But nobody does that, but that's what you should do. Hydrogen peroxide, 12 seconds, 0.3 seconds, you can see. Kind of effective as hydrogen peroxide. Quaternary ammonium, 450 parts per million. To easily leave a residue, it takes a long time for it to kind of go away. Same with oxide gas, 500 milligrams per liter is not that much. 2.4 minutes, but to detox, you got to let it evaporate even longer. It takes a long time. 10,000 milligrams per liter, 25 hours to get rid of the influenza virus with ethylene oxide. So it's probably not a good method to do unless you're just sterilizing a room or something like that. So the halogen chlorides, or chlorine is a halogen. Mode of action, the compounds combine with water and release this hydrochloric acid that's temporary, but it's very effective. It denatures enzymes blown apart, and it's a good one. Iodine is also good. Interferes with metabolic functions and disulfide bonds and that sort of thing. Can be irritating to the skin. Hydrogen peroxide, oxygen forms free radicals, and it oxidizes. It's pretty good, hydrogen peroxide. The only problem is, you notice it's brown bottle, and if it's exposed to too much sunlight, it essentially turns into water. So you got to be careful about that. Phenol, carbolic acid, the old famous surgeon that used that during surgeries. He had an improved surgery success rate because he sprayed carbolic acid at the top of his surgical room and cut down on infections. The only problem was, of course, everyone had irritated skin at the end of the day. Chlorhexidine, complex organic base containing chlorine and 2 phenolic rings. Mildness, low toxicity, effects on virus and fungi are variable. It's a good general purpose pre-scrub or something like that for surgery. Alcohol, it's used the skin we already talked about. You got to let it sit there for a while, and of course detergents is that factor that just blows membranes apart. Good old hand soaps and things are really good. So just to remember that the disruption of structure is a loss of function. So structure and function go together, but anything that destabilizes the structure of, let's say, proteins or enzymes and bacteria, it will cause a loss of function. So that was me in my younger days. So the idea is you want to have a compound that has a dual charge, and it essentially goes and embeds itself in membranes and tears them apart. And so that's what these are just representing, that we have a positive and a negative sort of end to each, and that gives that by effect of disrupting whatever the membrane is. Other agents like dyes active against gram-positive because they just clog up the area that we know that stains positively with various dyes when we do the gram staining, and it's very effective. Acids and alkalis, very low, very high pH, can destroy cells. The problem is it may damage some of the things you're trying to use. And then, of course, there's things that we use on surfaces and injectables, and controlling microorganisms are the antibiotics, and if we had regular normal semester, we'd go into more of the antibiotics and things like that, but unfortunately that's not going to be the case. So this is the end of this chapter, and I'll go through that material, and I will be providing a take-home exam here shortly for the rest of the semester for exam 3, and then we'll roll into the final and we'll be done. And hopefully it's not been too painful, but we have one of the hardest areas to go through, of course, is our discussions on antibodies and the like. So we'll stay true to the agenda, but let's see where we go. I think we have, what, 3 more chapters? I'll have to go look. Anyhow, have a good day.